So today I'm going to tell you a little bit about our recent research. This title is actually suggested by one of my theory collaborators at Rensselaer Polytech Institute. And so basically what he said is that if you look at the exciting topics today in condensed matter physics, and most of the materials actually are involving this chalcogenide compounds. Okay, I can name a few here. For example, topological materials, including topological insulators, wire semi-metals, ion-based superconductors, and the recently emerged the topic of two-dimensional ferromagnets. If you look at it, you can see, all of them are chalcogenide compounds. However, today, I'm going to focus on two material systems that we have been working on recently. One is the two-dimensional transition metal dichalcogenides, exemplified by moly disulfide. And the second is so-called chalcogenide perovskites. You probably never heard of this term before, but I'll explain what they are. So the first topic I'm going to discuss is this proximity effect on this 2D chalcogenides. Since Buffalo and Waterloo, they are in close proximity, right? Transition metal dichalcogenide is actually a large family of materials with a chemical formula of MX2, where M are these transition metals, and X are these chalcogens such as sulfur, selenium, and tellurium. They actually span a large range of physical properties from superconductors, metals, all the way to insulators. Today I'm going to focus on these semiconducting family, such as moly disulfide and tungsten diselenide. These are layered materials. So within the layer, they have strong, covalent bonding, and in between the layer, they are connected by these weak van der Waals interactions, and therefore you can easily peel them like graphene, right, to make a monolayer. And in fact, if you look at the structure, they do look like a graphene. So I'm going to tell you why we are interested in this monolayer of transition metal dichalcogenide. Okay. I apologize that my talk is more geared towards the physicist, so I understand that the audience has a diverse background. If you have any questions, make sure you raise them, and if there's some details that you are not clear, don't bother with it. Just understand why we do it, and what would be the material used for. So in the bulk, this TMDs are indirect bandgap materials. Okay. However, if you thin them down into a monolayer, it becomes a direct bandgap material with their band edge states. So the conduction band minimum and the valence band maximum both move to the K points of the Brillouin zone. Okay. And so it becomes a direct gap. Now, in the monolayer, the inversion symmetry is broken. The consequence of that is it actually leads to two inequivalent yet degenerate valleys. What I meant for that is that these two valleys, okay, the valley means the energy extremum points, okay, and they are energetically degenerate. So these bands are at the same energy levels. However, they are inequivalent because they have large difference in their momentum. Okay, and these materials has very strong spin-orbit coupling, and the result of that is that there will be spin splitting of these band edge states. Okay, so for example, in the valence band, you have the top band becomes spin up, and the bottom band becomes spin down for the conduction band, for the valence band maximum. So initially it's a single band, and then once you have this spin orbit coupling, splits into these two with opposite spin characters. And the splitting is actually very large, on the order of 100 millieV to 400 millieV. And in the conduction band, there's a similar splitting of these bands, but at a much smaller energy scale, on the order of a few millieVs. And because the spin-orbit coupling actually preserves time reversal symmetry, you will actually have coupled spin and the Valley degree of freedom. What I meant by that is that if you look at the energy levels with the same energy in different valleys, okay, those if you have the energy level in the K valley to be spin up, then in the other K valley, the other valley, K prime or negative K valley, the spin is down. Okay, so your spin index and the Valley index, they are actually locked together. And this is what made this material particularly interesting. You know, people proposed using the Valley, index, Valley degree of freedom for quantum computing or classical information processing. Now, so that is what people call it Valleytronics. Okay, so basically Valleytronics means using the Valley degree of freedom for information storage and processing. It's much like in spintronics, where you use spin degree of freedom for information storage and processing. So to realize this vision, you actually need to prepare the Valley polarized state. And you need to be able to detect the Valley polarization, and you need to be able to control it, okay, to be able to switch it. Okay? Now, because these Valley states, they are energetically degenerate, the only way to access certain state within a valley is using circularly polarized light. Okay? For example, if you use left circularly polarized light, you will be able to access the K valley, and if you use the right circularly polarized light, you will be able to access the other valley. Now that, of course, is not good for device integration, right? So for high density array of devices, you would like to use electric control. Okay? So to realize this electric control, first step you need to do is to break this Valley degeneracy. How do you do that? Now, because this Valley degeneracy is protected by time reversal symmetry, so in order to break the Valley degeneracy, you have to break the time reversal symmetry. Okay? If you have some basic background in magnetism, you know that the easiest way to break this time reversal symmetry is by applying a magnetic field. Okay? So that's exactly what people have done in the past couple of years. So this is a work done by Tony Haynes' group, then at Columbia University. So they basically applied a external magnetic field, and they measured the excitonic transitions within the K and the K prime valleys. And they observed this energy shift of the excitonic transitions, as the field is applied. And what they see is that this energy changes linearly with applied magnetic field. And what's the magnitude of this changing energy? It's about 0.2 millieV per Tesla. Okay? Now, this energy is actually pretty small compared to the thermal energy, KBT. Okay? If you think about computing, right, you want to use the computer in room temperature, not in a fridge. That means you want energy scale to be increased, to be comparable to KBT or even larger than that. Okay? So how do we increase this energy splitting? The obvious way is to increase the magnetic field. Okay? So instead of doing it in a conventional lab, you actually go to the high magnetic field lab in Los Alamos, where you can apply a field more than 60 Tesla. Okay? And that is the work done by Scott Crook's group So again, they measure this energy shift as a function of magnetic field all the way to more than 60 Tesla. And you can see a linear change in energy as a function of B field. Okay, I forgot to mention there are actually two excitonic transitions. We label that as the A exciton and the B exciton. Okay, they correspond to these splitted energy levels. So A exciton corresponds to lower energy excitonic transition, and the B exciton corresponds to higher energy transition. Now, if you look at the energy shift for both A and the B exciton, you can see they not only have the same sign, they also have the same magnitude. I want you to keep this in mind because I'm going to talk about later what will be the difference when we use other effects. Okay? So of course, not everybody can afford a 60 Tesla magnetic field, right? And that also is not compatible with device integration. You need to find other ways to enhance this value splitting. Okay? Now, as a person with a background in magnetism, so what we have thought is to replace this external magnetic field with an internal magnetic field. So using the exchange effect from a magnetic substrate. So that's the proximity effect I mentioned in the beginning. Okay? So exchange field is what's keeping the spins parallel to each other. So that's what makes a ferromagnetic material, right? You have a ferromagnetic iron or cobalt. The spins are aligned parallel to each other because of this exchange interactions. And this field can be on the order of a few hundred Tesla or even 1,000 Tesla. This can never be achieved, in any of the lab facilities. Okay? So this is the effect we are going to use. So when we thought of this idea, we immediately try to search for, references to see if other people have already thought about this. And at the time, we didn't find any reference, but 1 year or 2 years later, we saw this publication from Chen Niu's group at UT Austin. Okay, so they did this theoretical work. They put this moly ditelluride onto a European oxide substrate, where European oxide is a ferromagnetic insulator. And according to their calculation, they get a Valley energy splitting of up to 44 millieV. Okay, so that's actually equivalent to a magnetic field of 220 Tesla. All right. So indeed, at least theoretically, this proximity effect works. In fact, proximity effect is nothing new. People have known this for years. For example, you have proximity effect in superconductors. If you put a normal metal onto a superconductor, the interface of the normal metal also becomes superconducting. And there's also other, proximity effect. For example, in this work published by MIT Modera's group, they put this topological insulator, which is Guoxin is working on, onto the European sulfide substrate, where this European sulfide is another ferromagnetic insulator. And what they observe is that this material introduces ferromagnetism in the topological insulator, which originally is non-magnetic. And what's very interesting is that although European sulfide is a ferromagnetic material only at low temperatures, below 20 Kelvin, the magnetism within this topological insulator actually persists all the way to room temperature. Although this result, is still being debated. Okay, so why we are interested in European sulfide? First of all, it is an insulator. We want an insulator so that we don't mess up with the transport of the 2D materials. Okay? And secondly, it has a large exchange coupling constant, and combined with a very large magnetic moment from the rare earth, you will have large exchange splitting. Okay? So we decided to use this material. Luckily, we have the collaborator, from Waterloo who can provide this material. Okay? So that actually end up, make our work a success. So first of all, we need to grow these transition metal dichalcogenides, okay, because at that time, the exfoliated samples is too small for our optical measurements. So we use a method that is slightly different from a conventional CVD method. So basically, we first using E-beam evaporation to grow an ultra-thin layer of moly trioxide. And then we use this sulfurization method to convert this oxide into moly disulfide. If we can control the condition right, we can actually control the morphology of this transition metal dichalcogenide. From this isolated triangles, all these triangles are monolayer single crystals, okay? To this merged triangles all the way to a continuous thin film that is monolayer with nearly no overgrowth and nearly no voids. Okay? So of course, just seeing it from the microscope is not enough. People typically use two techniques to characterize a monolayer transition metal dichalcogenide. One is this Raman spectroscopy. Okay, so there are two modes. One is called E2G mode, and one is called A1G mode. The separation between these two modes are very sensitive to the film thickness. Okay, so for the monolayer, it's only order of 20 wave numbers, and for bilayers, it's actually above 23. So you can use this separation to characterize whether the film is a monolayer, a bilayer, or multilayers. The other is, as I mentioned, as the film is thinned down to monolayer, it converts from an indirect gap material into a direct gap material. And so the photoluminescence actually becomes much enhanced in monolayer. Okay, this is different from a conventional material where you have more material, you will have more photoluminescence, right? So we use this mapping of the Raman modes and the mapping of the photoluminescence intensity in different areas of the film to confirm that this is indeed a monolayer. And we also did some quick check using some simple electric transport devices. Okay, so we measure the photocurrent. Okay, we shine light to measure the photocurrent, and we see that the photocurrent actually scales with the size of the device. Okay, so we ensure that this monolayer is a continuous monolayer. And once we have this high-quality monolayer, we need to actually transfer it onto a ferromagnetic substrate because the original film was grown on a sapphire substrate. Okay, so transferring is actually pretty straightforward. We follow this reference, and essentially you actually coat a polymer such as PMMA or polystyrene on the surface of the transition metal dichalcogenide, and then you actually scratch the edge of the film and then add a water droplet. Utilizing the different hydrophilicity between the film and the substrate, you actually peel this film completely. And then you can transfer it onto a different substrate and dissolve the polymer to get a clean film. And then we use the Raman and the PL again to confirm the transferred film has good quality. And then to measure this energy shift I mentioned, we use optical techniques that is called Magneto-reflectance. So essentially, we measure the reflectance spectrum, and at the same time, we apply a magnetic field. And we use left and the right circularly polarized light to get information from the K and the K prime values, respectively. All right, so without going into details of the setup, I'm going to give you the results. Okay, I'm going to skip this one. So essentially, this is a typical reflectance spectrum. Okay, remember this is a monolayer material supposed to, absorb very little light, right? But surprisingly, because of the strong light-matter interactions, for a single layer, it actually absorbs 10% of the incident light, which is amazing. And we are going to focus on the low energy transition. We call it A exciton. So A exciton is this transition here, right? B exciton is this one. Okay, so here are the results. First, let me show you the reflectance spectrum for tungsten diselenide on a non-magnetic substrate. If you do not apply a magnetic field, as I said, the K and the K prime values are energetically degenerate, right? So the reflectance occurs at the same energy. When you apply a magnetic field, you can start to see a shift of the reflectance. Sigma plus the left circularly polarized light corresponds to transition in K valley, and the right circularly polarized light corresponds to transition in the K prime valley. And you can see that one shifts to higher energy and the other shifts to lower energy. Okay, this is measured at the 7 Tesla, so we can get the value of the energy splitting, and this is actually consistent with the previous measurement, which has a order of 0.2 millieV per Tesla shift, right? Now, once we put this material, 2D material, on a ferromagnetic substrate, we actually see similar trend, right? So sigma plus shift to lower energy, and the sigma minus shift to high energy. The only difference is that the magnitude of this shift is much higher. Okay, so you have an enhancement in the energy splitting. So to prove that it is an exchange effect from the magnetic substrate, we need to measure the field dependence. Okay, so here I'm showing you the field dependence. So this is on non-magnetic substrate. We get a linear relationship between the splitting and the magnetic field. So the slope is 0.2 millieV per Tesla. However, when you put this 2D material onto a ferromagnetic substrate, you see this nonlinear behavior. And at low fields, the slope is much higher, on the order of 3 millieV per Tesla. Okay, so you have more than an order of magnitude enhancement in this energy splitting. You can think of this ferromagnetic substrate as a magnetic field amplifier. Okay? Now, to ensure that this is an exchange effect, we need to roll out spurious effects such as dipole interactions, right? So how do we tell that this is indeed the exchange instead of dipole interactions? Remember that exchange is actually a very short-ranged. It's within atomic distances. On the other hand, the dipole-dipole interactions is long-ranged. Okay, so to distinguish this effect, we actually insert a non-magnetic material in between this ferromagnetic substrate and the 2D material. And by that, we should be able to cut this exchange completely. However, the dipole interaction will still be there. Okay, so we see whether this effect is still there or not, whether we still have this enhancement. So here are the results. So when we insert a 10 nanometer non-magnetic spacer in between the 2D material and the ferromagnetic substrate, we see that the curve falls on exactly that of a non-magnetic substrate. That confirms that this effect is indeed the exchange effect, and dipole plays no role here. All right? Now, because this is an exchange effect, the magnitude of the energy splitting should be proportional to the magnetic moment. And we know that magnetic moment is not only a function of B field, it's also a function of temperature. Okay? So we measured the field dependence of the energy splitting at a few different temperatures. Okay? As I said, this energy splitting should be proportional to the magnetic moment. So we can also measure the magnetic moment as a function of B field at the same temperature. Okay, so that's the second set of experiments. So you can start to see the similarity, right? Both the field dependence as well as the temperature dependence. Now remember, these are two completely different experiments. This is the energy splitting measured by reflectance. And this is a magnetization measured by a vibrating sample magnetometer. Okay? Now you see the similarity. Okay? In fact, I can scale the two. So what I did here is basically normalize the saturated value of energy splitting and the magnetization at 7 Kelvin. Okay? That's all I did. And all the data points of the energy splitting fall onto the magnetization. There's no fitting parameters here. Okay? Once you see this data, you should be able to convince any skeptical referee that this is indeed an exchange effect. So we also measured the Valley energy splitting as a function of temperature at a fixed magnetic field, and compare that to magnetization as a function of temperature, and we also see this one-to-one correspondence. Okay? Next, we need to understand where this Valley splitting comes from and how that's different from the effect from the external field. Okay? So our theory collaborator at University of Nebraska, Rena Sobyanov, did this first principles calculations. Okay, so this is the supercell he used. So he assumed a 111 oriented European sulfide substrate, and that's how the supercells match with the 2D materials. And these are the calculated band structures. You do not need to worry about these details, because what is relevant are just these band edge states, which I'm going to show you in the next, right? So these are the band edge states, relevant to the optical transitions. And these are the bands for the A exciton, and these are the bands for B exciton. Without exchange field or external field, these energy levels are degenerate. They're at the same energy level. Okay? Now when you turn on the exchange field, at the K prime value, both the conduction band minimum and the valence band minimum actually rises up in energy. Okay? And these are the calculated values. And for the K value, you actually have the opposite. So both bands actually shift down in energy. Of course, what we are interested in is the energy difference between the optical transitions. So the energy difference between sigma minus and the sigma plus light. Okay? Since we have all the values for these energy levels, we can easily calculate those. Okay? So this is the transition energy for sigma minus, and this is the transition energy for sigma plus. And the energy difference is on the order of 10 millieV. Okay? So this is of the same sign to our experimental observation. Our experiment has a value of on the order of 3 to 4 millieV. And that's about half of the value of this theoretical calculation. This, of course, is understood because we do not have a perfect interface to start with. Okay? So whatever happens at the interface, contaminations, non-perfect match will reduce this exchange effect. Now, what is interesting is actually the calculation on the B exciton. Okay? Remember, in the beginning when I show you the results from the other group, both A exciton and the B exciton have the same magnitude and the same sign of the energy shift. Right? So now let's look at the result of the B exciton transition. So according to his calculation, that the conduction band and the valence band actually shifts in opposite directions. And that is totally unexpected. Because if you apply a external magnetic field, you will have this Zeeman splitting. They will shift in the same direction. Okay? So what is the difference between an external field and an exchange field? Well, for the exchange field, you will have both ferromagnetic exchange and antiferromagnetic exchange. And they are in opposite directions. Okay, so what this calculation is showing you is that for the conduction band and for the valence band, the sign of the exchange are actually opposite. One is ferromagnetic, the other is antiferromagnetic. Okay? So for the K valley, of course, they shift in opposite directions. And as a result, when we calculate the energy difference between the sigma minus and sigma plus, it is actually negative. Okay? So which means if you measure the valence splitting, you should get a different sign for the B exciton than the A exciton. Right? That's totally different from the external field case, where you have both the same magnitude and the same sign. Now, what's the reality? Okay, so we measured recently the B exciton transitions. And indeed, aside from this more noisier data points, because the B exciton transition is a lot broader, you see this inverse slope. Okay, suggesting that this B exciton do have the opposite sign. So we are very happy about this consistency between the theory and the experiment. So you may ask, what's next, right? Once you have an enhanced valence splitting, what can you do with this material, right? That's really the most important thing. Okay? So I can use this cartoon to show you what we can do with this. Okay? If you can look at this, mountains and the floating mountains as the conduction band and the valence band, right? Once you put a ferromagnetic substrate, you actually valence split these states, so they are aligned at different energy levels. Now, you can actually use an electric field to tune the Fermi level, where these electron C actually occupies the highest level where these electrons occupy, so that you can control the Fermi level at the appropriate position. So for example, in this case, you will have this holes that only occupies one of the valleys. Okay? So that means 100% valley polarization. And because this valley and the spin, they are coupled together, 100% valley polarization also means 100% spin polarization. Okay? So that is actually the first important goal to realize this Valleytronics, right? You have to have valley polarization. Okay? And you have to be able to manipulate it. The way to manipulate it is by shifting this Fermi level, by applying an electric field. So you use electrical means to tune it instead of using optical means. Okay? So we are working towards this goal right now. So any questions so far for this topic? Because I'm going to shift gear to talk about something that's totally unrelated to spin. Okay, so here's a short summary. I don't want to read it. So the work is done primarily by these graduate students, Chen Zhao, Tenzin Norden, and Peiyao Zhang. And this is a collaboration between 60 institutions, including these Chinese universities, University of Nebraska, who provided the theory support, and the University of Waterloo, Guoxin Miao's group for providing the magnetic substrate.
I have a question here.
Yes.
May I ask?
Sure.
So is the adjustment of the valley splitting or these tuning, is it possible also by means of chemical doping or functionalization or something of that sort?
So whatever ways that you need to do, you have to break the time reversal symmetry, right? So I do not think conventional chemical doping will be able to break this time reversal symmetry. However, doping can indeed induce this breaking of the time reversal symmetry if the dopants are magnetic, right? So it's the same thing. if you dope magnetic elements and let them couple, so it becomes ferromagnetic, then it's effectively adding an internal magnetic field. Okay, so we actually worked on this. We started from this doping and this magnetic substrate simultaneously. But turns out that the substrate effect is a lot easier to realize.
So maybe along those lines, a couple of questions. So even if you do have a magnetic doping, you would still have to rely on some form of long-range interactions. To
very good, yes,
right?
yes.
Otherwise, you end up with ferromagnetic centers, which
paramagnetic centers.
Could be actually, decay very quickly with
That's right.
So I don't know if that would help you actually with this.
That's why it's so challenging to do magnetic doping, right? Because you have to have high enough concentration to induce this long-range coupling.
Right.
Yeah.
Right. And so do you see any prospect of it, similarly, say, to DMSs?
It's possible. It's possible, yeah. So we are still working on it. Other groups are also working on it.
Oh, I imagine.
Yeah.
And so one final question. I'm sorry I'm holding you here.
No problem.
We're on topic. With europium sulfide, that's really an interesting idea. But from the sort of purely practical point of view, Curie temperature is killing you.
Very good. Yeah, very good question.
So you'd still like to go, something that
the reason we went with European sulfide, as I mentioned, is because, first of all, it's an insulator.
Right.
We do not have a lot of choices for ferromagnetic insulators. Most of ferromagnets are metals, right?
I know.
And so of course, we are thinking along the line how to improve the magnetic properties of it, improve the Curie temperature, and also change the orientation, easy axis orientation of the magnetic materials, right? So you can realize this.
Graphically and isotropically.
Right. Yeah. All right. So I'm going to go with the second topic. We are working on this very interesting material called the Chalcogenide perovskites. Okay, and we are trying to pitch it to the funding agency. This is an emerging class of semiconducting materials, very different from conventional semiconductors. Why? So if you look at this conventional semiconductors, starting from silicon, and then to this gallium arsenide, indium phosphide, and all the way to 2,6 materials and those casterite or all these materials, they are derived from the silicon structure with this four-fold coordination, right? So these are all covalent materials. Now, recently people have been working on this organic-inorganic hybrid perovskites for photovoltaics, right? Within a short, few years, the efficiency of these solar cells shot up from 3% all the way to above 20%. So this is an amazing material. And this material is different from this conventional semiconductor because it's non-four-fold coordinated. It's actually ionic. Okay? So it looks like it's a magical material for photovoltaic applications. Why haven't it appeared on our rooftop yet? Turns out that it has very severe drawbacks. Okay? Number one is its stability. If you toss this material into water, it just dissolves like salt. Okay? It's also not stable against heat, light, or electric field. On the other hand, it also contains toxic elements such as lead, which people don't like, right? So what we are thinking of is whether we can learn from this material, why it's amazing, why it has very high efficiency for photovoltaics, okay? And then address this stability as well as the toxicity problems, okay? So then we can have a perfect solar absorber. Now, if you look at this perovskite, okay, it actually contains this, organic molecule, okay, as one of the atom in the perovskite, right? Perovskite has a chemical formula of ABX3. So here, A is actually an organic molecule, and B is a group 2 element, and this X is this group 7 element. For a physicist, you know, the perovskite we know of, we are very familiar with, actually those oxides. Okay? However, oxides are not known for photovoltaics. Why? Because its band gap is too high. It's an insulator, right? So now, if you can replace this oxygen by, you know, the elements down in the, you know, periodic table, sulfur and selenium. Now, according to the first principles calculations, the valence band maximum of these oxides come primarily from the oxygen 2p states. Okay, so if you replace this oxygen by sulfur with 3p state and the selenium with 4p state, they are actually deeper in energy. So these valence bands are raised up. And that way you can actually narrow down the band gap. Okay, so that's our naive thinking. So if we can make these into chalcogenides, that's why we call it chalcogenide perovskite. Then we should be able to narrow the band gap, make it absorb in the visible region, which is where you know, the majority of the solar spectrum come from. So when we come up with the idea, we searched for references again to see whether people have already done this material. And not surprisingly, you know, people have done it more than half a century ago. And interestingly, by a company in Niagara Falls. Not the Niagara Falls, Ontario, but Niagara Falls, New York. Okay? And so our theory collaborator, Shen Bai Zhang's group at RPI, they did the first principles calculations. And they screened 18 compounds of the chalcogenide perovskites. And what they found is that a large group of materials will have the suitable band gap for photovoltaics applications. Okay? So if you look at this green band here, okay, this band gap value will give you the solar cell efficiency above 30%. If you relax this requirement and go to this band, it will still give you an efficiency, theoretical efficiency of 28%. Okay? And in fact, these materials, they actually crystallize into different structures. One is distorted perovskite. The other is a needle-like phase. They are just basically different distortions. And the other is a hexagonal phase. For hexagonal phase, the band gap is very small. So it's more or less metallic. And this distorted perovskite has the highest band gap. Okay? Of course, only having a right band gap is not a guarantee of a good solar material. What are the other requirements for a good solar absorber? It has to be able to absorb light very efficiently, right? And it has to be able to transport charge carriers very efficiently. Okay? So they did the calculation for the imaginary part of the dielectric constant, which is essentially how this material absorbs light. Okay? And if you look at this, these different curves, they represent different materials. And this yellow curve is this calcium zirconium selenide. This is the perovskite structure that I talked about. And if you compare it with these well-known solar materials, such as CIS, gallium arsenide, and within this band gap range of 1.8 eV all the way to 3 eV, this perovskite material actually has the strongest light absorption. Okay, this is not surprising because theory predicts it's a direct band gap material. Okay. On the other hand, 90% of the solar cells are made of silicon, and silicon is an indirect band gap material. So it does not absorb light very efficiently. Okay. And you know, the theory cannot tell you directly how the material transport charges. Okay, what it tells you is the effective mass of the charge carriers. So that gives you an upper limit of how fast these electrons and holes can go. Okay, the larger this band dispersion, you know, the more steep of these curves, the higher the carrier transport. Okay, so turns out that this material is quite unique. So if you look at the band dispersion in different directions, x, y, and z, in both x and y directions, the band dispersion is pretty large, which means the carrier transport in these directions are very good. On the other hand, in the z direction, the band is pretty flat, which means the effective mass is large, the carrier transport is slow. Okay? So that means this material, in theory, should be able to combine very good light absorption with pretty good carrier transport. And this is not typically available in a conventional material. Because these two requirements are typically contradictory to each other. If you want strong light absorption, you need very high density of states. If you have high density of states, you will have very flat band dispersion. Okay? So, you know, that's theory. And then we need to do experiments to verify it. Okay? So we did this synthesis actually following the recipe developed more than half a century ago. Okay? We used this CS2 gas to sulfurize the oxide to make it, convert it into chalcogenides. I'm not going to bore you with detail of the synthesis. I'm going to give you the results. Okay? So we first synthesized the bulk powder form of these materials. So these are the starting oxide material. You can see they are white, suggesting they have large band gap. They do not absorb visible light. And once you turn them into, a sulfide material, a chalcogenide, it becomes black, which means, you know, it absorbs visible light, right? And its composition is close to 1:1:3, so that's the required for the perovskite structure, which is shown schematically here. So this structure would give you a X-ray diffraction pattern like this. So we compared our experiment with this standard spectrum, and they show very good match, suggesting that we do get the right phase. We also did Raman spectroscopy, and Raman is also very sensitive to the structure of the material, right? And we compare the experimental spectrum with the theory calculated spectrum. So theory is able to find the 24 active Raman modes, while experiments we found 14 of them matched almost perfectly to the theoretical calculations. On the other hand, if you go to the oxide, you do not see any feature within this wave number range. Okay? Now, of course, what we are more interested in is the optical properties to see if the band gap indeed is as theory predicted. So now we use the UV-vis spectrum to measure the optical absorption, and we see a sharp transition at around 600 to 700 nanometers. And we use the so-called TOC plot, okay? Essentially plotting this h nu, which is the energy of the photon, times alpha, which is the absorbance, as a function of the energy. And we can see a more or less linear behavior at the band edge. We can extrapolate it to 0 to extract the energy band gap. And this is on the order of 1.75 electron volt. And the theory gives us a value of 1.73. So this is actually a very good match. Okay, we also observed a very strong photoluminescence from this material, suggesting that this is indeed a direct band gap material with very strong light matter interactions. Now, as a semiconducting material, we want to be able to tune its band gap. How do we do that? we can actually use alloying, right? We can either use this anion alloying or cation alloying. So by anion alloying, I mean replace these sulfur with, for example, oxygen, right? Partially. So we can actually have different ratios between oxygen and sulfur. So this will become barium zirconium oxysulfide. By tuning this composition between oxygen and sulfur, we are able to systematically tune the band gap, okay, from 3 eV all the way to 1.7 eV. Okay? Now, for photovoltaics, a single junction cell, the optimum band gap is actually only order 1.3 electron volt. So instead of increasing the band gap, we want to narrow the band gap. How do we do that? So instead of using this anion alloying, we can actually use cation alloying. Okay? If we replace partially this zirconium with this 4D state on the conduction band with titanium with 3D states, we can actually shift down the conduction band and thus narrow the band gap. Okay? So before we do that experiment, we actually did something else. We actually measured this Raman spectrum at high pressure. Okay, we collaborated with Bernie Weinstein's group in our department to do this measurement. Okay, and we can see that these Raman modes as a function of pressure is actually linear. All the way to the highest pressure his diamond cell can apply. And there is no phase transition. What that means is that this perovskite structure is stable up to this high pressure. Okay? Why is it important? Well, because titanium actually has a smaller atomic radius, right? So by doping titanium to replace zirconium, you are actually applying a chemical pressure. Okay? It's effectively as applying external pressure, right? So this way, we have demonstrated that, at least from this point of view, that incorporating large amount of titanium is possible without changing its structure. Okay. In fact, you can actually calculate theoretically how this unit cell volume changes with pressure. Okay. So by this applying above 10 gigapascal of pressure, you actually can compress the unit cell to that of unit cell of barium titanium sulfide. Okay. Now, they also measured this band gap as a function of pressure, and they do see as you increase the pressure, the band gap actually reduces. Of course, this is scientifically interesting but practically useless. Nobody is going to use a solar cell at high pressure. We need to do doping, right? So we did titanium doping, okay? This is the X-ray diffraction pattern, and we actually blow up this 1-to-1 peak, and we see as we increase doping concentration, the X-ray diffraction peak actually shifts to higher angles, which means actually the lattice actually shrinks, okay? And this is the calculated D-spacing. Above, 10%, we actually have phase separation. So we no longer have a single phase material. Now, how does the band gap change? That's what we are interested in, right? So we again use the UV-vis spectroscopy, and we use a TOC plot to extract the band gap, and plot that as a function of doping concentration. And we see as we increase the doping concentration, the band gap actually indeed decreases. What's very interesting is that, just by a tiny amount of doping, about 5%, we are already able to reduce the band gap to 1.45 eV. That is very close to the optimum range for a single junction solar cell. Okay? So we are very excited about this prospects of this material in photovoltaics. And right now, we are focusing on producing thin films. And making devices out of these thin films to see what kind of efficiency we are going to get for a device. Okay? So I think that's pretty much it. I'm not going to repeat the summary. And the work was done by Samantha Pereira, and that's my graduate student. And Hao Hui is an exchange student from Xi'an Jiaotong University. Okay? And the work is supported by US Department of Defense, National Science Foundation, and Department of Energy, as well as SUNY Research Foundation. Okay? And with this, I would like to finish, and thank you very much for your attention.
Well, thank you very much.
Sure.
Wonderful presentation.
Thank you.
I already heard a number of questions in the middle, so I'm hoping we have the. It's nice to have some lunch together, so I have a good perspective of where you're coming from Nebraska and SUNY. So you have an opportunity here to interact with some colleagues, and so do you with our guest speaker. So if there's any questions, please. The floor, please.
Nature of the devices that you're potentially going to use these thin films in, or can you elaborate a little bit about what's the potential applications that you're potentially going to use these films in?
One is the photovoltaics, right? Thin film solar cells.
Yeah.
So essentially, right now, the red hot field in the photovoltaics, almost everybody is working on these hybrid perovskite, right? As I mentioned, the drawback of this material, it's by nature. People can, sort of address it, but they can never solve this problem completely. So by replacing this hybrid perovskite, organic material, by this totally inorganic material, we hope to solve this stability issue as well as the toxicity. Okay, and the other is, of course, this is not only maybe not only suitable for photovoltaics, but for other optoelectronic applications, right? Because you can systematically tune the band gap, and it has very strong light-matter interactions. One of the strongest material I've ever seen. So, yes.
To replace this material for photovoltaic application, is the cost-wise, are they comparable, or is it a little bit like more?
The hope is that this thin film material is going to be more cost-effective than silicon, right? Because silicon is an indirect bandgap material, which means it does not absorb light very efficiently. Then you have to use very thick material, right? By thick, I meant 180 micron. Now, if you use this thin film material, you can go down to 1 micron. So you save a lot of material, in terms of material cost, right? What's the economics of this? For example, you have to use thin film deposition, right? And that is still an unknown question, right? People have also produced the thin film solar cells. They are in fact commercialized, right? CDTE, CIGS. However, the dominating product you see today is still silicon. Yeah.
So what is the mechanism that displaces selenium with titanium in the process of you doping it? How does the titanium displace the selenium in a way that gives you a new material?
Sorry, the titanium doping is to replace zirconium.
The zirconium, yeah.
Yeah.
So how does it displace one atom by another atom in the lattice?
So basically, what we did is this, high temperature powder processing,
Yeah.
right? So you mix this different oxides, barium titanium oxide with barium zirconium oxide, and during the high temperature process, they actually react to form a alloy, sort of, right? So it's randomly occupying the lattice sites of this, B site. Okay, it's basically a solid state reaction. Yeah.
So is the role then on titanium mostly to control the internal pressure, or it also changes the entire band structure at the same time?
Right. So, first of all, when you lower the volume, you should see the effect of band gap reducing. But the primary effect comes from this 3D states, which is lower in energy than the 4D.
Right, yeah.
Okay.
So the reason why I'm kind of getting at this is, if you can control the surface chemistry through surface stress, surface strain, possibly even just surface bonding, you could potentially also control that pressure of that sort of component of external pressure type thing, or how the material feels, the pressure essentially to manifest, that surface chemistry through as external pressure. Is that something that would be viable looking into?
That's certainly an interesting,
Because you can go to sufficiently small domain sizes, and essentially your surface effects would then take over.
So you are more thinking of this kind of heterostructure, right?
Not so
where you
much
have
in
this
heterostructure. So for example, and that's one of the aspects that we worked on in oxides. You have rutile anatase, for example, in the case of titania, or
right, yeah.
in the case of indium oxide, and effectively by changing the size, you can mimic that external pressure.
Yes.
To sort of manipulate the
Right.
So obviously we would have to go to smaller domain sizes. I don't know how small we can access, but that could be one of the possibilities to sort of manipulate that component.
Right. So basically, you are talking about different crystallized size with different structure, and then you can mimic a certain pressure.
That's right. Based on surface structure and surface chemistry.
Right.
Basically.
Yeah, certainly, I think that's possible.
Could be, right.
Yeah.
The other. I guess it all boils down how difficult it is to control the size.
You can control the grain size. That's not a problem.
Okay.
The only thing is that for photovoltaic applications, you actually prefer to have a big grain size.
Yeah.
Okay, microns. Yeah. So you reduce the effect of pressure, right?
Pressure, right.
Yeah.
It might be orthogonal in that sense. Yes.
Yeah. Yes.
Just early of the first off, was really interesting.
Thank you.
And then I just wondering, like, how big it continues within a sulfide film you guys really can grow?
We can grow 50 micron, no problem. Occasionally, we can get 100 micron.
Okay.
Yeah.
And another question is, I noticed that I don't remember, like, by changing whatever parameters, you can actually have like domains and turn into continuous film.
Continuous film, but that's a polycrystalline film with different orientations of these single crystals.
Yeah, sure.
Yeah.
I was wondering, did you ever try to measure PL signal on those, like, not continuous film? Did you ever?
Yes, we did. Yeah.
That also can give pretty nice PL signal, or?
Actually, it's stronger.
It's stronger?
Yeah.
Oh, that's
Yeah. Mm-hmm.
Okay, thank you.
Mm-hmm.
Excellent. Any other questions for our speaker? Please join me in thanking our speaker for a great talk.
Thank you.
Thank you very much.
Thank you.